Hey, good evening. We're live on YouTube. This is a part 2 of lecture 13. A quick reminder that we're going to have our quiz number 3 on October 20, which is a Tuesday, and that is 2 weeks from now. So we're going to review some properties related to function and relations. Provide a simple counterexample to the following proposition, where every function has an inverse. Can you draw a counterexample with an arrow diagram of a function that does not have an inverse? Okay. If you think about it, what is the one that does not have an inverse? That means if I try to take the inverse, it's no longer a function. Then what is the property of a function? Recall a function f from x to y, where x is a domain and y is a codomain, associates with every input in x, one and only one output in y. So this statement has a few important points. Associate every input in x to one and only one output in y. So what does that mean? That means the following type of arrow diagram is not allowed. So this is not a function. So for inverse to not exist, that means the inverse is not a function. So what example? This is a particular example. I have two elements mapped to the same element in the codomain. Two elements in the domain mapped to the same element in the codomain. If I take the inverse, hypothetically, if I try to take the inverse, I get something like this, right? Because I revert the arrow. And then this is not a function, which means the inverse does not exist. What are some other examples of inverse does not exist? If I have a function where my codomain has an extra element, if I take the inverse, which I revert the arrow, I have this yellow element right here that is not mapped to anything. So again, this function don't have an inverse. So let's record some definitions. A function is onto if for every element in the codomain, there exists some element in the domain. So f from A to B is onto if and only if for all element in the codomain B exists an element in the domain A such that B is equal to f of A. A mental picture to have, right? If this is AB, for every single element B in the codomain, there's some form of arrow that points to it. So there's always something in the domain that maps to it. Second definition is a function is one-to-one if nothing in the codomain is the output via two different inputs. Another way, if fx is equal to fy, then x equal to y. Remember, equivalently is if x is not equal to y implies fx is not equal to fy. Of course, it's for or xy in A. And finally, a function is one-to-one correspondence if it's both one-to-one and onto. Alternatively, we call one-to-one to be injective, onto to be surjective. One-to-one correspondence means bijective. Now we're going to look at some recipe to prove a function is one-to-one. If I want to prove something is one-to-one, we start by giving a pair FA is equal FA1 is equal to FA2. And with some information, we want to demonstrate A1 is equal to A2. Okay, so simple example. Show the function fx is equal to 5x plus 7 is one-to-one. As I mentioned, the proof sketch is, let's say, let fx is equal to fy. We want to show x is equal to y. So let fx is equal to fy, which means 5x plus 7 is equal to 5y plus 7 by substitution. Minus 7 from both sides, we have 5x is equal to 5y. Both divided by 5, I have x equal to y. So I just showed if fx is equal to fy, x is equal to y. Now let's look at, so this is a detailed way of writing it down. Now look at the practice problem. Again, I want to show this to be one-to-one, but now it's a little bit more complicated. A is a Cartesian product of sets. C is a set of integer, which is a positive factors of 144. So what is 144 if I factor it? If I factor it out, it's actually equal to 2 to the power of 4 times 3 to the power of 2. And you can verify it offline. We want to show this is one-to-one. What do we do? Again, we want to let fx1, y1 is equal to fx2, y2, where x1, y1 is an input pair. We want to show the pair equal to each other, which means we want to show x1 is equal to x2, y1 is equal to y2. Okay, so by definition of f, because fx1 equal to fx1, y1 is equal to fx2, y2, we have 2 times xy times 3 times y1 is equal to 2 to the power of x2 times 3 to the power of y2. And somehow we want to arrive at the fact that x1 equal to x2, y1 is equal to y2. So what does this mean? I have on the left-hand side a factorization of some number. And on the right-hand side, I have a factorization of some number. And both are factorizations of 144. But we want to show that there essentially is a unique way to factor out the factor out 144. Okay. So at the center of this is the fundamental theorem of arithmetic, or it's called unique prime factorization theorem. By unique prime factorization theorem, which is also called fundamental theorem of arithmetic. Every integer bigger than 1 is either a prime number or it can be represented as the product of prime numbers, and this representation is unique up to the order of the factors. So by applying this theorem, there is a unique way to factor the number 144. We have x1 equal to x2, y1 equal to y2. Therefore, x1, y1 equal to x2, y2. Therefore, the function is 1 to 1. So there are some interesting things related to the size of a set with respect to the function. So if I have a function f mapped from one set to another, and a and b are both finite set of size m and n, if f is 1 to 1, then the size of a is smaller or equal to the size of b. If it's onto, then size of a is bigger or equal to size of n. If it's 1-to-1 correspondent, which is bijective, then those two are equal. So of course, what is a mental picture? This is a picture of a function that is 1 to 1. So you know on the left-hand side, there's 3 elements, on the right-hand side, there's 4. Because one of the elements on the right-hand side is not mapped to anything. There's nothing mapped to it. What is onto? On the left-hand side, there's 4 elements, right-hand side, there's 3 elements, where the first 2 elements on the left-hand side map to a single element on the right. So in this case, the size of the set on the left is bigger or equal to the size of set on the right. And if it's 1-to-1 correspondence, which means it's a bijection, one to one and onto, which means it's a 1-to-1 correspondence, then the size on the left is equal to the size on the right. There is a version of a pigeonhole principle. If there's a function mapping from one set to another, and there have to be finite sets, if m is bigger than n, then f is not 1-to-1. What does this mean? If m is bigger than n, but every element in A has to map to every single element, have a map to some element in P. So that means I'm taking m element and put it into n different containers. At least one of those containers is going to have 2 elements. And this picture is what I'm talking about. If you have this, the function is not 1-to-1. So there is a definition of a invisible function. A function, also invertible function, sorry. A function is invertible if there is an inverse. And turns out 2 sets has the same size if there exists an invertible function between them. And if we want to show a set is infinite, if there exists a function that is 1-to-1 but not onto. So this last bit is a really interesting property, and that might be useful in proofs. For example, I want to show the set n, which is a set of natural number. If I want to show this is infinite, we can design a function fx is equal to 2x. And we know this function is 1-to-1, but not onto. So why is that? Every little element on the left is mapped to an element on the right that is twice. So 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6. But on the right-hand side, I have element 3, element 1, and so on and so forth, where nothing is mapped to. So this function is not onto, but it's one-to-one. So it's a way to show my set N is infinite. So in order to do that, you just need to design a particular function such that it's mapped to the set A to itself, and it's one-to-one but not onto. Now we have an interesting theorem here. Given two sets, if there's a one-to-one function from A to B and a one-to-one function from B to A, then the sets have the same cardinality. Right? This is slightly different than the previous one, which is rely on inverse. In this case, if A to B is one-to-one, B to A is one-to-one, we can show that they have the same size. In addition, we also have the property for every set A and a power set do not have the same size. Remember, the power set is all possible subsets. Let's double check in the extreme case where if A is equal to empty set. If A is equal to empty set, the size of A is equal to 0. But the size of the power set of A is equal to 1 because it has empty set at this element. So there's at least one element. So 0 is smaller than 1. So they don't have the same size. So now let's review some of the property of a relation. If I have a binary relation, it's reflexive if A and A is in there. If we have an arrow diagram, every element has a self-loop. Now, it is symmetric, or if it's anti-symmetric, if the pair AB is in a relation, but the pair BA is not in the relation. In other words, the arrows goes only one direction. So it's not bidirectional. Transitive, whenever there's a relation between AB and the relation between BC, we have a relation between AC. Okay, so those are some of the mental pictures. Now the next interesting question is that if I give you the one set arrow diagram, not the two sets, one set arrow diagram, what kind of property do they have? Remember, we just reviewed, if it's reflexive, it has to have a self-loop. If it's symmetric, it has to have bidirectional edges, and so on and so forth. Okay, so let's look at look at R1. Does every element has a self-loop? Yes, so it's reflexive. Let's look at R2. Does every element has a self-loop? Yes, so it's also reflexive. Same thing with R3. Does every element has a self-loop? The answer is yes, it's reflexive. This is time you should actually pause the video and try to solve this on your own for the next 5 minutes. Now I'm going back to R1. I'm going to say, is this symmetric or anti-symmetric? Remember, anti-symmetric means that there's no double edges or double arrows, right? So arrows goes only in one direction. Is that true? Because A goes to D, but D does not go to B, right? This does not exist. B goes to C, but C does not go back to B. So this means it's anti-symmetric. Let's do the same thing for R2. Whenever A goes to D, D goes back to A. B goes to C, C goes back to D. So those are bidirectional things or double arrows. So that means this is actually symmetric. What about the third one? The third one, whenever A goes to D, I actually don't have D go back to A. when A goes to C, I don't have C goes to A, and so on and so forth. So this is antisymmetric. Now let's go back to R1. Let's say if it's transitive. Remember, it's transitive whenever A goes to D, A goes to B, B goes to C, then A goes to C. So for example, if A goes to D, D goes to D, A goes to D. B goes to C, let's use a different color. When A goes to D, D goes to D, A goes to D. B goes to C, C goes to C, B goes to C. So no matter how much I check, this is a transitive relation. Let's look at R2. Is this transitive? Whenever A goes to D, D goes to D, A goes to D. Whenever A goes to D, D goes to A, then A goes to A, and so on. I can again check through, and then we know that this is transitive. Finally, look at R3. Whenever A goes to, A goes to C, C goes to C, then A goes to C. When A goes to B, B goes to C, A goes to C. So no matter how I check, again, I have transitive relation. So I have R1 and R3 to be both RAT. Remember, what does RAT stand for? It means it's a partial order. Okay. A relation is a partial order if it's reflexive, antisymmetric, and transitive. Again, if it's a rat. So let's recall what is a Hasse diagram. There's a few rules that we reviewed in part 1 of lecture 13. If you don't remember what is a Hasse diagram, please try to go back to that lecture. Essentially, a Hasse diagram does not have self-loop, and it also omits some of those transitive relations to try to reduce the size of the diagram. For example, this is a Hasse diagram for the relation. Again, this is discussed in part 1 of the lecture, of lecture 13. And then here's another Hasse diagram among the elements of a power set. Now, our last exercise is if I give you an arrow diagram, one set arrow diagram, to try to draw the Hasse diagram. First thing you do is to eliminate all the self-loops because it's implied. A Hasse diagram applies to a relation that is red, which is a partial order. So it's by default, by definition, it's reflexive. So we assume that we're going to omit some of those loops, and then you're going to remove all those transitive relations. If I do that, what I get for this example is A goes to, well, let's redraw it. Same way. I would do A, because A is a lower element, it goes to D. B is a lower element, goes to C. And that's it. So what is the idea to do this? Number 1 is to suppress the loops. Number 2, use lines, not arrows. And go from low to high. Rule number 3, only have an edge between A, B, where A is low, B is high, a line between A, B. If there exists no C in my set that sits between A and B. So this is just to omit some form of transitive relation. So if I have hypothetically, if my arrow diagram looks like this. My corresponding Hasse diagram is this, because we are omitting the transitive relations. So that means there's only a line between AC if there's nothing between. But in this case, there's B that sits between A and C. So there's no edge line between AC in the Hasse diagram. Now follow the same rule. Let's simplify R3. First of all, remember the first rule is suppress the loops. So I get rid of all the loops. Second of all, so I'm going to do the intermediate step. This is just intermediate steps, okay? So first of all, I'm going to get rid of all the loops. This is what I have, but this is not a Hasse diagram yet. The second thing is using lines, not arrows, going from low to high. So I'm going to get rid of all the arrows. But I need to redo it low to high. Well, like A is the lowest. But now the third one, well, low to high, but then you get rid of the arrows. But we're not done yet because we need to remove anything that has something in between. So we need to remove this highlighted edge, AC, because there's something in between, which is B. So the final result, the proper Hasse diagram looks like this. Okay. All right. That's it for today's lecture. Have a good night.